1986, I was kind of doing voluntary work for my uncle at some children's summer camp in Indiana. It's like, I get my history with the US goes a long way. Right. So I got an email from Brian Conrad last night going, about Frobenius. And I was like, what? So Brian has been like watching, hi Brian. Apparently Brian was watching the live stream and had something to say about my normalizations for class field theory. So there's email from Brian Conrad. I stuck it on the website. I really think I should be blogging this. So email from Conrad. About this normalization. I can't remember which way on website. There's two ways to normalize it, and I chose the way that somehow people like Deline and Rappaport and Langlands choose, because they know what they're doing. But Brian somehow knows why. So. Right. So my next goal is to kind of state, so it's all working towards a statement of the local Langlands conjectures. So sort of vaguely speaking, they're going to look like this. So the local Langlands conjectures for GLN over K, so K over QP finite. I should say that pretty much everything I've said so far does also work for K, the field of fractions of a power series ring over a finite field. But I just feel less confident talking about it. The local Langlands conjectures for GLN over K say vaguely speaking, say that there's some bijection between some kind of n-dimensional representations of some Galois group, they're supposed to be something to do with representations of GLN of K. So that's kind of where we're going, but we've got to the point now where I've introduced most of the terminology we need, and I can begin to start talking about this left-hand side. So obviously we need to be more precise than this. I want to make a precise statement, and I want to say a lot about. I'm going to make a precise statement, and I'm going to spend in the next couple of days. I'm going to talk about the case n equals 1 and n equals 2, and kind of convince you that these things are true in those cases. So that the left-hand side, this is not a Galois group at all. This Galois group is somehow much more closely related to this Weil group. I mean, it's a Weil-Deline group, really, which is something to do with the Weil group. So somehow the Weil-Deline group, in some sense, it's very closely related to the Weil group. So the whole point of me waffling on like this is we need to start talking about n-dimensional representations of the Weil group. So the conclusion is, so the upshot, we need to start talking about representations of this Weil group. And then later on we'll figure out what a representation of a Weil-Deline group is, and then we'll really kind of understand what's going on this side of the story. Right. So this is where we're going today then. We're going to talk about representations of this Weil group. So what is this Weil group? So recall, this Weil group looks like this. We have this inertia group. So K is always a finite extension of QP, and then we have gal K bar over K to Z hat to 1, and then here we have a Z living in here and there's our V group. And then there's still the same I k bar over k. And you would imagine, really, that we were really interested in representations of this Galois group, right? If you know anything about, if you've ever seen something like étale cohomology, you see étale cohomology of a variety over K comes equipped with a representation of the Galois group of this Gal K bar over K. Or if you've ever seen the Tate module of an elliptic curve over K, that Tate module is going to be an L-adic representation of this Galois group. So these representations of this Galois group do kind of fall out of the sky sometimes. And the first kind of slightly pedantic observation I want to make is that we're not going to talk about these. We're going to talk about representations of this V group instead. But the trivial observation is that if I have a representation is just a group homomorphism to GLN of something, right? So if I've got a representation of this guy, then I get a representation of this guy just by restriction. And somehow the converse isn't quite true. If I have a representation of Z, it might not extend to a representation of Z hat because it somehow might not, there might be some issue extending it by continuity. Somehow Z is a dense subset of Z hat, and if I define some random map on Z, how do I know for sure it will extend to a random continuous map on Z hat? So in fact, by considering representations of the V group and not the Galois group, we've actually, we see everything we're interested in and some more stuff as well. And the extra stuff we see is quite controllable, really. So let's talk about representations of the V group. So they're going to go to GLN of a field, so we have to choose what the field is, and at this point, the field can be anything. Okay, so let's represent. Well, so I'm going to talk about V representation. Well, I mean, rather than keep telling you what I'm talking about, but I just curses, I've done a bad thing. Sorry. There might have just been a horrible noise on some. I'm just switching my phone off. Right, so representations of a V group. So let's let E be a field. Let E be a field, any field you like. And this V group has got a topology. And so it'd be nice to talk about continuous representations, but if it is a random field, then it probably doesn't have a topology. But we kind of want it to have a topology, so let's give it the discrete topology. Let's put discrete topology. On E. And also, just to be clear, and also on GLN of E, right? Where I've got some n at least, whatever. So we'll choose some n. GLN of E is now a group. And so now let's consider rho from the V group of K to GLN of E. That's going to be an n-dimensional representation of that V group. A continuous group homomorphism. So I'm dressing it up so it looks like topology, but it can't really be topology because I've put the discrete topology on this. So what does continuous mean in this context? I've got a group homomorphism to a discrete group, and that's supposed to be continuous. And I guess the identity element in this group is open because every subset's open. So the preimage of an open set is open. So continuity seems to imply, and in fact is equivalent to kernel of rho being open. So that's kind of interesting. Kernel of rho is open. So let's try and figure out what's going on. So what's going on with this inertia group? Let's look at the restriction of rho to this inertia group. So rho of ik bar over k. So again, we'll use the language of topology. This is a continuous image of a compact space. A compact space. So it's compact. So it's a compact subgroup of GLN of E, which is a discrete group, right? Compact subset of the discrete set GLN of E. So if it's compact and every set is open, then it must be finite, right? Because it's covered by its points, and the points are open. So there must be a finite subcover, so there must only be finite many of them. So rho of inertia is finite. And that's it, really. So conversely, conversely, if I've got some random map and the kernel is some open subgroup of I k bar over k, then the image will be finite. I don't know. So this is quite cool, because remember, what is this Weil group? This Weil group is the easy part, which is Z, and then the really hard part, which is inertia. But we've put ourselves in a situation where the hard part is finite. So it's only somehow, we've got a finite amount of difficulty to deal with. And of course also, I guess, the image is finite, so it somehow cuts out some, it'll cut out some extension, somehow WL, I guess. I haven't defined WL if it is some arbitrary extension of K, but there's going to be somehow the kernel of this will be related to some extension of K for which the inertia is only finitely ramified. I guess I don't need to worry about it at this point. So there we go. So we've got a continuous group homomorphism. The image of inertia is finite. So that means we can attach some numerical invariants, right? So hence can attach we can use the theory of of this filtration of the lower. We can use lower numbering, right? On the image of inertia. There. So this is going to be finite. So by the fundamental theorem of Galois theory, we've got KNR, remember. Here's the maximal unramified extension of K, and here's K bar. There, and the Galois group of this is I K bar over K. And now we have a finite quotient of this. So this corresponds to L, and I guess this is the Galois group here will be rho of I K bar over K. There. L, this obviously depends on rho, right? And of course, this is finite, so L over K might be infinite, but at least the inertia subgroup is finite. So therefore, rho of I K bar over K is now, we have notation for this now, it's I L over K. And of course, now this contains I L over K, comma 1 contains ... This is the lower numbering, right? So let's define f of rho. So this is going to be the conductor of rho. This is some measure of the ramification. So of course the conductor of rho. And the definition is this. It's a sum that looks like it might be infinite, but which isn't infinite. So f of rho equals the sum from I is 0 to infinity. We look at an index. We have I L over K. And we look at the index of I L over K, comma I. So that's some, this is some positive integer. So this is some rational number. Now we need to multiply it by something else. Multiply by the dimension of what? V divided by V I, oh dear. Dimension of something, and the something is V divided by V I L over K I. So here, what is V? V is the V is the underlying vector space on which this group is acting. So where I've got a row from this V group to GLN of E, which I'm now going to write as aut EV, right, with V is e to the power n. So of course I'm just using standard notation. I've got this group acting on this vector space. So this finite group here, I L over k comma I, is acting on this vector space here, and that's just the invariant. So maybe I'll just sort of notation. If I've got H to or to V, then VH is the fixed point, is the V in V, such that HV is V for all H in H. So there's a definition, but it looks like an infinite sum so far, so we better check it's not infinite, because if it's an infinite sum, I have to worry about topologies and things. So let's just note that the sum is finite. Why is the sum finite? Because as if I is very large, then remember this is the lower numbering, right? This implies that I, L over k, comma I, is just the group with one element. Right? This filtration goes all the way down to the bottom. If I is very large, then this is one element, and this implies that the dimension of V over V I L over k, comma I, is 0. Because you see, this is just V again. The thing's fixed by the identity is just V. So the quotient is 0-dimensional. So this is actually a finite sum. It's a finite sum, so then what's clear is that f of rho is a rational number which is at least 0. And I think it can be 0, right? Can it be 0? Those fractions are always positive because they're the reciprocal of some positive integer. So if I want this sum to be 0, I guess every single dimension had better be 0, which means that V had better be fixed by I L over k, comma I for all I, which I guess means that V has to be fixed by I L over k, comma 0. I think that just means that I L over k is trivial. Right. So I think f of V, so that's clear, and also easy is that, I think I've just convinced myself at least, easy is that f of rho is 0 if and only if rho is unramified. Which means what? Rho of I k bar over k is just the trivial group. Or the trivial n by n matrix or whatever. So there's an easy exercise. Now my memory, although I haven't written it down, my memory is that f of rho is always an integer. Isn't that how life works? I think it's... Yeah, I'm going to stick my neck out that I think... So if memory... this must be true. Remark. F of rho is actually an integer. I guess the proof of that uses things we haven't talked about at all. Here's a sketch of how I think the proof of this goes. I think you can check it's an integer if the image of rho is abelian by some explicit calculation, and then you check it's true for general rho by using some kind of cheat to... you check that kind of f is preserved when you do induction, and then you check that every representation is a z-linear combination of representations induced from characters. So I think there is some work here. I don't think this is an exercise. This is the kind of thing you have to go and look up. Unless I'm missing something. So there we go. So now we have Now we have the notion of a representation of a Weil group. And we also have some random invariant attached to this representation. I guess I should finish by remarking, note that f of just to give you I'm trying to give you some kind of feeling as to what f of rho does. Where's the definition? Let me just figure out what the first term is. I L over k comma 0 is just the same as I L over k. So I just want to remark that f of rho is the dimension of V quotiented out by the invariance plus the sum for I at least 1. I'm just knocking off the first term and just showing you. So you see, here's a very trivial way to get a lower bound for f of rho. Like if I is really kind of big and complicated and moving V around, if the restriction of rho to this inertia group turned out to be a complicated, irreducible representation with no invariance at all, then this would be 0, and so already you get the dimension of V at least. So there's just some trivial lower bound for f of rho that's sometimes useful. So there's that. Oh, so maybe we should do examples. Let's do a one-dimensional example. So RL. So recall we have this map RK, which is an isomorphism of K star with WK ab. And of course, WK ab, by definition, is a quotient of WK. And this has a topology, and this is continuous, and this is a topological isomorphism. So we get an induced map here, you see. So there's a very natural map from the Weil group of K to K star. And so if I can think of a representation of K star, then I can think of a representation of WK, you see. So let's think of some representations of K star. I guess, recall we have a valuation map. VK, that goes from K star to Z, right? It's only a uniformizer to 1. But if you know anything about local fields, you'll see that sometimes we use the valuation and sometimes we use the norm. And the norm's a very handy thing to have around. It's a very geometric thing. Satisfies the triangle inequality. So I don't think I've ever mentioned it. So let's introduce the norm now. Let's introduce a norm on K. I want to define kind of the norm of lambda equals some small number, some small real number, to the power of minus V of lambda. So that's how norms work, right? So for example, when you do the p-adic numbers, the very beginning you learn about the p-adic numbers, and you have to decide what the norm of P is. And normally in books, people say the norm of P is going to be 1 over P, right? So is this wrong? Yeah. Sorry, this is wrong then, isn't it? I want the norm. Let me just check. I've gone off notes, so I need to be careful. K is QP. V of P is 1. I want the norm of P to be 1 over P. So, yeah, this small real number is going to be 1 over P. Right? So e.g. if K is QP, right, the V of P is 1. And so we want maybe the norm of P, the norm of P is usually kind of P inverse, right? Which is kind of P inverse to the power of V of P. So in this case, you see, we have a lot of choice here, right? We have a lot of choice here for that small real number. This is why I've been sticking to this is kind of a stupid technical point, but I just remember being confused about it when I was a graduate student. The valuation, there's no arguing with it, right? I'll send, if I want this to surject onto Z, I'll send the valuation to be uniformized, it can be 1, and that's kind of normalized in some pretty sensible way, right? But for the norm, there's some notion of norms being equivalent, right? Take any, as long as this small real number has to be less than 1, right? I think that's all we need, right? If we choose different choices for epsilon, give us different norms, but the norms are equivalent, right? Lead to equivalent norms. Okay? And now often in math, if you ever decide to learn things like non-Archimedean analysis, like rigid geometry in the sense of, in Tate's original sense, then you tend to start off with a non-Archimedean field, a field complete with respect to a non-Archimedean, non-trivial non-Archimedean norm, and you really never really care about that norm other than up to equivalence. So from the point of view of kind of doing geometry, we don't really care which small real number we use. And there are plenty of situations where there's no canonical choice, right? So here's let me just do some interludes. I'm going to make a meal of a very technical point because it was a technical point that never dawned on me for years. And I'm kind of pleased this is another example of something I wish they'd told me when I was your age. If I've got some random, if K is any field, kind of complete with respect to a non-trivial, non-Archimedean valuation, non-Archimedean norm, then that's enough to set up some theory of rigid geometry. We can set up a theory, a good theory of, say, whatever, rigid geometry, for example. And we don't really care what that norm is. So here's an example, e.g., here's a random field which is complete with respect to a non-Archimedean norm. Let's take the complex numbers, and now let's look at kind of power series in one variable t, right? Well, let's call it z. I don't know. Let's call it t. There's power series string in one variable, so this is kind of like meromorphic functions defined in a neighborhood of the identity there. And we can define, there's an obvious valuation on this, right? We could define the valuation of kind of t to the n plus higher order terms. The valuation of t to the n plus higher order terms could be n, right? That's a pretty sensible definition of valuation on this field. So the valuation of 0 is plus infinity, as usual. And then for any other function, we expand it as a power series. This means power series. And we look at the first non-zero term, the order of vanishing of this function at 0, the order of the 0 or the order of the pole, and that's a good valuation. Great. So once we've got a valuation, we then need a norm. If I actually want to start talking about the size of things in K, so how am I going to define? How am I going to decide? How am I going to decide what this notion of size is, right? So now I need a norm. I want a norm on K. Right, I'm going to say the norm of some function f is now going to be some small number epsilon to the power of the valuation of f, right? For some naught less than epsilon less than 1. So which epsilon do I choose? Any epsilon will do, right? So epsilon is obviously a real number, right? The norm of something is going to be a real number. So I can choose it. Any epsilon will do. And furthermore, it would be nice to choose a canonical epsilon, right? So you kind of guarantee that you've chosen the same one as the other guy that's also working on the same area. You're writing a joint paper with someone else, and you kind of want to. But I don't think there is a canonical one, as far as I know. There's no canonical one. So you basically have to decide how small. If the valuation of t to the n is n, the idea is you're supposed to be thinking of t as small, right? These things are power series; they're supposed to converge in a neighborhood of 0. So you're supposed to be thinking of t as small. So I want to find the size of t to be some small number. But I don't really care what small number it is. So there's how norms work on general fields complete with respect to a norm, right? But we actually are in a slightly different position, okay? So let me just show you something funny. In our situation, with k over qp finite, there is actually a canonical norm. And I didn't really realize this for a long time. And the reason there's a canonical norm is because the residue field, kind of kk, is finite. And that residue field being finite, that implies that k is locally compact. Right? Because so explicitly, the integers of k is just isomorphic to zp to some degree, d the degree of k over qp, and this is compact. So I found a compact open neighborhood of the identity. So this feels locally compact. And if it's locally compact, it means there's an additive Haar measure. So this additive Haar measure is a way of, giving a size to subsets of k, right? So that implies there exists some additive Haar measure on k. I mean, that's somehow a big theorem that for some generally locally compact Hausdorff-Abelian group, there's some canonical measure on this group. But we don't need it. I don't want to invoke some fancy. You believe in things like Lebesgue measure on the real numbers, right? So similarly, if I can just tell you what a measure is, then we don't have to invoke some abstract. If I just tell you what measure I'm thinking of, then things should be fine. So let me. So let's call this Haar measure mu. So the idea is that mu of some open set is going to be a real number, or maybe if that open set is really big, it might be infinity. Like the mu of k is going to be infinity. Mu of compact things is going to be finite. So mu of the measure of OK, that's going to be finite because OK is compact. So it's going to be less than infinity, and we can always normalize this Haar measure. So let's say the measure of OK is 1. There we go. So I've got this random measure that's fallen out of the sky, and I can measure the size of subsets of k. And let's say the integers of k. That's a nice subset to take because it's compact. You know that Lebesgue measure, like you can't measure the reals, that's just everything. But you can measure closed 0, 1, that nice compact subset. That's kind of a finite measure. So there we go. Let's say the measure of OK is 1. So I wonder what the measure of P, what's the measure of P? Well, I don't know. I haven't even told you what Haar measure is, right? So how can you possibly work this out? But let me tell you, one property about Haar measure, the point about Haar measure is invariant. So Haar measure, what defines Haar measure is that the measure of x is equal to the measure of x plus a, right, for all a in k. This is why this is an additive Haar measure. It's translation invariant, right? Okay, Haar measure is translation invariant. So that's like, for the real numbers, that's like the measure of the closed interval from 3 to 4 is the same as the measure of the closed interval from 0 to 1. Because you get from one to the other by adding 3. So there we go. So now if you're thinking, you realize that actually you can work out the measure of pk now. Because another fact about measures, of course, if I've got two disjoint sets x and y, right? Also, of course. So that's to do with it being a Haar measure, but just a measure. Also, we know if x intersect y is empty, then the measure of x the measure of x union y is the measure of x plus the measure of y. So there's random facts about measures, and now that's enough. So now note that OK is actually a disjoint union of lambda in the residue field, kind of lambda tilde plus pk, right? Where lambda tilde is some lift of lambda. OK mod pk. It's a list of this thing to OK. You see, this is just the fact that this quotient group here, OK mod pk, is some finite set. So this is a finite disjoint union, right? And so therefore the measure of OK is going to be Q times the measure of pk, where Q is the size of the residue field. So there we go. So if you want to kind of stay sane, you can normalize this measure so that the measure of the full ring of integers is 1. And now we know what the measure. Maybe I should say these measures are all real valued, right? So therefore, mu of pk is 1 over qk, right? So now here's the really cute idea. Here's the really cute idea, which I learnt about in Tate's thesis. Here's the idea. If A is in K star, then let's define the norm of A to be the factor by which A scales Haar measure. Multiplication by A scales Haar measure. So that's the trick. So I occasionally mention the real numbers. The real numbers are also a perfectly good locally compact Hausdorff topological abelian group. And so the real number should have some Haar measure, which is just the usual measure on the real numbers. So here's what I'm saying. So e.g., if K is the reals temporarily, then we could just let X be closed naught 1, right? And the measure of X is 1. And now you give me a random real number, let's say lambdas in the reals is non-zero. Now let's scale it, right? I want to define norm of lambda by the norm of lambda. It's just the measure of lambda times x. You see, so you take something that did have measure 1, you scale it with lambda, and you see what the measure is now. And you see, this is a sensible, if you think about it, e.g., if lambda is bigger than 0, then lambda x is just 0 lambda, right? And therefore, the measure of lambda x is lambda, you see. And so we see that the norm of lambda is lambda, right? And if lambda is less than 0, the same calculation, if lambda is less than 0, then we multiply close naught 1 by lambda, we get an interval that now has length negative lambda. You see that lambda equals negative lambda. So you see, we've recovered the usual notion of norm on the real numbers using some ridiculous measure theory. But what I'm saying is the same trick works here. And this is really important for Tate. Tate goes through this. If you do it for the complex numbers, you don't get the usual thing. Here's what fun exercise. Work out. Compute the norm for Z, a complex number, using this method. So these this is the very cute thing. Harm measure is only defined up to some positive real scaling factor, but you see, this method doesn't mind, right? Strictly speaking, if you like, I could define the norm of lambda to be the measure of lambda x divided by the measure of x, right? For any x which had non-zero measure, you see. I'm trying to see how much lambda scales things. So there we go. So you could compute the norm of Z for Z a complex number using this method. And the stupid thing is it's not the usual complex norm, as Tate observes. So let's get back to K. Let's get back to K of a QP finite. I'm trying to figure out what the measure. All this interlude is because I'm trying to figure out what the sensible norm on K should be. So the big question is, we know that the valuation of pi k is 1, right? And I want to define the norm of pi k to be some small number to the power 1. But now the question is, what's this small number going to be, right? And what I was trying to say at the beginning is, for a random non-Archimedean field, a random field complete with respect to some norm, like power series in one variable over the complex numbers, you can just basically choose that small number however you like. But because we're in this situation where a Haar measure exists, see, there's no Haar measure on that power series ring over the complexes because it's not locally compact. The complexes kind of has the discrete topology, and the maximal ideal somehow has infinite index. Anyway. This thing is locally compact, so we should be able to get an answer. So you see what we've done. So in our situation, use this Haar measure trick. And we see that the size of OK is 1 there, and so I want the norm of pi to be the measure of pi times OK, and that's the measure of pk. Oh, this is pi k, sorry. pk. And we worked that out, and that was 1 over q. So that's it, you see. I've done some nonsense, and at the end of it, I've come up with a notion of the size of pi k, and it's a small number to the power 1, but it's somehow a canonical small number. So there's my canonical notion of size on Q. And you really have to do this kind of thing carefully if you're proving things like what's that thing called? The product of all the norms is 1. If I want to define, there's some norm on the Adele groups, and I want to check that the norm of any global thing is 1. The product formula or something. So there we go. So what's the upshot? There's a natural norm on K, right? And here it is, it's the norm, and it goes from K to it goes from K to the non-negative reals. Of course, the norm of 0 is 0, but for a non-zero thing, and if lambda is not 0, the norm of lambda is going to be 1 over q to the power of v of lambda. Right? And this 1 over q, my argument is that this is a very canonical thing. So there we go. So I will often write it like this. The norm of lambda is q to the minus vk of lambda, right? And where vk is normalized, so it's surge x onto z. Okay, so that's the norm I want to put on k star. And one nice remark is that actually the norm of lambda, so this norm map actually goes from k to the non-zero rationals. Because remember I was talking about representations of a Weil group at some point, and I said I wanted to take values in an arbitrary field of characteristic 0. So I don't really want it to be the reals, you see. So it's good that this is descended to the rationals. And of course, from k star, this goes to the positive rationals. And this is a group homomorphism, of course. Right? So now we have this kind of this map from WK. That's surge x onto WK ab, right? And this by class field theory is k star. And now I've just put a norm on this, and it goes to the positive reals. Positive rationals. So I get an induced map here, right? So I'm going to conflate the definition. So this is me. I'm going to use the same notation for two things. So this defines norm from the W of k to the positive rationals. Great. So there's our first example, right? So there's an example. So we can have E is Q, or any field, in fact, any field of any Q algebra, any field of characteristic 0. There, we've got this norm map from W of k to GL1 of E. And I guess more generally, we could just take the norm to the power n, right? There, for n in Z. These things are all representations. These are all representations of WK. They're all one-dimensional. I mean, I shouldn't call it n, because n was the dimension. Let me call it m. So there's some examples of representations of this Weil group. Maybe it's worth remarking that they all have... Remember we had this f. We could try and figure out what the f is. But I think we're exactly in this situation where f is going to be equal to 0. So a rather trivial exercise would be exercise. Check that f of this thing is 0. Right. So there's some examples of Wedeline representations. Oh, maybe I should also say, let me just check what is this thing here? Let me just, what's the norm of frob? So frob tilde, that's in the Weil group of K, and that lifts frob in Z, right? Which is you know what I mean by this Z, right? There's a canonical Z where the WK maps onto, right? WK surge X onto Z, and I choose generated by 1, which is frob, as it were. I lift this to WK. Well, we better just, I better just do this. I guess RK goes from K star to WK ab. And I think I normalized it so that pi k went to frob inverse, right? Oops. Or maybe I should say somehow pi k, I should be maybe OK star goes to frob inverse I k bar over k. Or I k ab over k, I suppose. So what am I going to do now? So frob inverse goes to here, and then by norm, the norm of pi k is 1 over q, right? So I think frob inverse goes to 1 over q. So I think I've just shown that frob must be q. I think that's what's happening here. Right. So I just do this to kind of orientate myself because people use different conventions. I should maybe warn you of this. I'm using the same conventions. A lot of this material is from Tate Corvallis. And I'm using, or attempting to use, the same conventions as he does. So maybe it's just worth remarking. I don't know if you've realised this, but I remark much of this is from Tate's article, Number Theoretic Background. In Corvallis, in Proc Simpos Pure Maths 38 or something. Am I just to assume nowadays that every kid has access to arbitrary? Do you all have like PDFs of this or access to PDFs? That's just how life works. Because I was going to say I've got a PDF of this which I can distribute, but manifestly this is ridiculously patronising. Right, so there we go. Now I think now is the time to talk about Wedelin representations. Okay. So let's talk about Wedelin representations. So this is actually one of the things that really shows up on one side of the local Langlands conjectures. So a Wedelin representation, so this is a slightly weird notion, at least on the face of it. A Wedelin representation is a pair, kind of rho 0, comma n. So rho 0, unsurprisingly, is a representation, just like we were talking about earlier. And n is going to be a nilpotent endomorphism. So what have we got here? So here we have rho 0 goes from the Weil group of K to Aut E of V. This is just isomorphic to GLN of V. Sorry, GLN of E. There is a continuous representation as before. So remember, E some field, discrete topology, and then V is isomorphic to e to the power n. But I think this time I better assume that the characteristic of E is 0, and the characteristic of E is going to be assumed to be 0. And the reason I'm going to assume that is because at some point I'm going to talk about this norm that I've just spent 20 minutes going on about. it's going to raise its ugly head again. And I want to take the norm of things in WK, and I want to think of them as elements of E, but they're really elements of positive rational numbers. So that's what row 0 is. And N is a nilpotent endomorphism of V. So this is the surprising extra piece of data, right? And N from V to V is an E linear. So it's just a linear map, and it's nilpotent endomorphism. Just to remind you, that means some power that means n to some power is 0 for all m large enough. Okay, so it's funny, you don't normally see those things when you're doing representation theory of groups, because groups have inverses. So row 0 of some group is going to be some invertible matrix, and this is clearly not invertible at all. So it's a pair row 0 and n. So you would imagine that there's probably some more to come, right? There's probably a relationship between row 0 and n. And let me write down the relationship. And we can all be slightly confused about why it's the right definition. So we've nearly finished this definition. We've got a pair, row 0 and n, and then there's one thing that links row 0 and n, and it's the following, such that for all sigma in the Weil group of K, the following crazy equation it holds. We have row 0 of sigma, that's a map from V to V, and we have n, that's a map from V to V, and then row 0 of sigma inverse, that's a map from V to V, because it's row 0 of open brackets sigma inverse. So that's a map from V to V, and it's going to equal sigma times n. So there's the definition. Don't ask me. Here's a great example. Examples. Just let row 0 be a representation. Did I say row 0 was continuous? Yeah. So row 0 be a continuous representation as before. Let's let n be 0. So this equation says 0 equals 0. So that works, right? So every representation is a Wedelin representation. And in fact, now, if you want to understand what's going on, clearly the exercise we need to do is we need to figure out one example of a Wedelin representation when n isn't 0. Because I guess, this might even imply that n is always 0, right? So what about an example with n not 0? Well, n is supposed to be a nilpotent endomorphism. Oh, let me make the following rather pedantic remark. Actually, we can deduce nilpotence from this equation, because this says, this equation, because I can choose something in WK whose norm isn't 1, right? Like, for example, I can let sigma be frob tilde. So then the norm of frob tilde will be Q, and so this says that n is conjugate to Q times n. So I've got a matrix which is conjugate to the matrix multiplied by some scalar. And of course, the eigenvalues of n, the eigenvalues of Q times n are just Q times the eigenvalues of n. So this says, for any eigenvalue, Q times the eigenvalue is also an eigenvalue. So the moment you have a non-zero eigenvalue, you have infinitely many eigenvalues. So all the eigenvalues of n must be 0, and that's enough to prove that n is nilpotent. So you can actually deduce nilpotent from that weird equation. But the interesting question is, can we actually think of any examples with n not actually 0? And of course, I've got one written down right here. So I want something that's nilpotent but non-zero, so the dimension of v is going to have to be at least 2, right? So let's say v is spanned by, let's let e be q squared. Let's let e be q, of course, and let's let v be q squared. Let's say spanned by E1 and E0. I would put E0 and E1, but I want n to be upper triangular. So this is the Q, so two-dimensional vector space over Q with basis E1 and E0. So I need to define rho 0. So let me define rho 0 of sigma is what? It's going to be the norm of sigma and then 1, right? That's going to be that's clearly a two-dimensional representation. It's just the direct sum. We've seen examples of one-dimensional representations of the Vega group, and I've just given you two, and I've just taken the direct sum of two of them. So by which I mean, so this is E1 and E0. So i.e. I'm saying rho 0 sigma of E1 is sigma E1. And rho 0 sigma of E0 is kind of sigma to the power 0. Is sigma to the power 0 E0. Right? That's the point about the notation E1 and E0. Sigma to the power 1 E1. And so now what's n? Let's define that n of E0 is E1, and n of E1 is 0. Okay, so n, if you want to think about the matrix, n of E1 is 0, so there's zeros here. And n of E1 is E0, so it looks like this. So if this works, then there's an example with n not 0. And now what's clear, it's manifestly clear that rho 0 is a representation, and it's manifestly clear that n's a nilpotent endomorphism, n squared is 0. So clearly what we've got to do is we've got to check that equation over there. So let's do that, and it's not hard. I guess so this equation, I don't know, it doesn't have a name. Let's give it a name. It's now called star. I wrote a paper with Toby G once, not about this stuff at all, and we had an equation that needed a name, and we just kind of looked at some big LaTeX list of all the symbols that were in LaTeX, and there's like a little telephone. So we called it telephone, and the referee didn't mind at all, and it got published with just a little picture of an equation labelled with a little telephone number. And I refereed a thesis 2 weeks ago at Warwick. This guy, Chris Birkbeck, I refereed his thesis, and his thesis was full of equations just labelled with really stupid symbols. Because he'd read this paper of mine, like there was a Batman symbol, there was like a little Zelda Triforce symbol, all these equations were just named completely insane things. And I just thought, this is absolutely great. And the other examiner was really cross, like a real moan in the examiner's report about all these stupid names. I don't know, I'm sticking with star. I don't want to mess with Loeffler. I've got to check that star is true. Let's check star. Because if star isn't true, then my notes are wrong. Rho 0 sigma, I want sigma 0, 0, 1 multiplied by 0, 1, 0, 0 multiplied by the inverse of this, 0, 0, 1. Let me tell you an amazing thing. Can we have a show of hands? I want to do a little experiment. Let's say I've got some 3x3 matrices. They're not zero, these are dots. I've got some 3x3 matrices. Okay, these are numbers, right? 1, 2, 3, 4, 5, 6, 7, 8. I'm going to write. There's two 3x3 matrices with the kind of annoying numbers in, right? And I'm going to ask you to multiply them together. So it's kind of a slight drag because multiplying 3x3 matrices together is a bit boring, but you've got to do it. And here's the answer, and you've got to write the answer down. Now, am I right in thinking that you all have an algorithm in your head for multiplying matrices together? Okay, and I would be very surprised. So when I ask you to do this with explicit numbers, the first number that you're going to write is that. Is that right? Everybody would go for the top left. So the second number that you write, when I learned at school how to multiply matrices together, I was taught a method by which the second number I would write would be here. Okay? When I multiply matrices together, I write the answer like this. Okay? And I've noticed when talking to people that some people, get this, some people when they multiply matrices together, they come out like that. They come out like a book, whereas I come out like a Japanese book. So can I just have a show of hands? Does everybody know what the answer is? When you multiply 3x3 matrices together, who would do, after star, which everyone does first, who does B next? That's really good. So who does A next? There are some people that talk this weird way like me. So the reason I mention this, what I've noticed is that when you actually have, so you see, I've got to multiply some matrices together, you see. And multiplying matrices together is a bit boring, but it's good to know tricks, okay? And one thing I've noticed is that I'm much better than most people at multiplying matrices together if the right-hand matrix is diagonal, okay? But I'm much worse than most people multiply matrices together if the left-hand one is diagonal. I'm really bad at this because I learned this other method. And so what I did, like when I realized this a couple of years ago, I learned the B method. I taught myself the B method. And now I can multiply on the left and the right by diagonal matrices really quickly. So it's something you should learn. So there you go. So I'm just going to do that. I'm really good at this, so I'm just going to do this. The answer to that, so the answer to that is 0, sigma, 0, 0. Right? And that's obvious because multiplying any matrix on the left or the right by a diagonal matrix is easy if you know how to do it. And indeed, that is sigma m. Right? So there's the exercise. Learn how to pre or post multiply by diagonal matrix quickly. So I'll tell you what the answer is. When you post multiplying by a matrix, all you do is you take the columns and multiply. Like that one, take the first column, multiply it by this, take the second column, multiply it by 1. When you're doing it here, you take the first row, multiply it by sigma, take the second row, multiply it by 1. So you see, this gets hit by, you multiply the row by sigma, and then you multiply this column by sigma inverse, and then we're finished. So there you go. It's very important you realise these things. It's like who's left-handed and right-handed. It's the same. This distinction. We're in two nice little groups: the A people and the B people. Huh? Yeah, but yeah. So I've taught myself to be ambidextrous. I can now do both. Just like my father. My father was left-handed, and in the school system in the UK in the 1940s, if you were left-handed, you'd have it beaten out of you. Like if the teacher saw him writing with his left hand, he'd get the cane on his left hand. So when he was at school, he had to write with his right hand, and when he was at home, he just wrote with his left hand, and ended up ambidextrous. And this was not an abnormal thing. Like somehow the left hand was the devil's hand. That's true in other cultures as well. I think, like in Italy, somebody was telling me that stayed true for quite a long time, till like the 70s or something. Anyway. So I've told you what a Veil-Delim representation is. So here's an exercise. Here's a more general example with n quite seriously nilpotent. I learned this from, again, this is straight from Tate Corvallis. If I have V if V is kind of Q to the N with basis E0, E1 up to En minus 1, and I define rho of rho 0 sigma of EI is sigma to the I times EI. And if I define N of EI is EI plus 1, I less than N minus 1, of course, and N of En is 0. And one checks that this works, right? And it's not just that this works. This is inside, if you can go ahead and try and classify what a general Wedelin representation looks like. And it turns out that this is some basic sort of indecomposable Wedelin representation. The N is like maximally nilpotent here. It's like zeros on the diagonal and one's just off. So you can take that representation, then you can tensor it with a random representation of WK, and then you can take direct sums of things, and that's it. That's how you build them all. I think sometimes people call this the Steinberg representation, or sort of STN. And so you can maybe look at the direct sum of ST of NI, kind of tensor rho I. And I'm pretty, somehow that's all, there's some classification theorem. Right, so there's Wedelin representations. Let me just tell you what it means to be semi-simple. It's a very natural place to stop. So we say a Wedelin representation is semi-simple. Oh, sorry, is F semi-simple. So this Wedelin representation, what we call rho 0 and N, it's called F semi-simple if rho 0 of Frob tilde is a semi-simple matrix. What does semi-simple mean? I.e. diagonalizable. Over E bar. It's not a coefficient field issue. I'll let you, if the eigenvalues aren't defined over E, I'll let you make E bigger. It's a semi-simple matrix. So nothing to do with N. You see, semi-simple normally means not nilpotent, right? Semi-simple normally means nothing weird going on in the upper right-hand corner, but these N's tend to be completely nilpotent. So it would be a bit ridiculous having this extra N and then demanding that N has to be 0. So this is independent of choice, right? Independent of choice of lifting of Frob tilde. That's not what it says here. I'm slightly. Now I'm panicking. Because I've just looked at my notes and it says something completely different. What's going on? Let's forget it. I'm going to go with that. I might want to reserve the... I've written in my notes where you say it's F semi-simple if rho 0 is a direct sum of irreducibles. Is that the same? Might be the same. Maybe I'll worry about that later. Maybe I'll worry about that in the 15 minutes that I'm about to have off. So it turns out that we're finally ready to state. So one side of the local Langlands conjectures bijections for GLN. One side is going to be the Wedelin representations. It's going to be n-dimensional F semi-simple Wedelin representations. Of WK. So there, finally, we have a completely rigorous statement. There's a set. Up to isomorphism, right? There's a set. And the local Langlands conjectures is going to say this set is canonically in bijection with some other set, and I'll define what the other set. So we'll define the other set in the. This is it's brief, so we can define it in the next half hour. So as I say, my goal by the end of today is to actually state the local Langlands conjectures in as precise a way that I can possibly manage. But here we'll have to, so now we're going to switch something. We're going to talk about infinite dimensional representations of G N of K. So it's a different story. Right, we have 15 minutes off, and then a short lecture, half an hour lecture, and then we're going on some terrifying walk or something. I don't want to go on at all. Have you got a question?
Does the C in LLC stand for
philosophy?
Correspondence or conjecture?
I don't know. It stands for philosophy. Don't know. Large Hadron Collider, it stands for. What is a conjecture? Is it something that has to be precisely defined? You see, I saw Tom Hales talking about the clay millennium problems. Hales is this guy that formalized he proved the Kepler conjecture, and there was some debate amongst the community as to whether his proof was correct. So he proved that it was correct by typing the proof into a computer proof checker. So he got interested in computer proof checkers, and he thought he wanted to state. He didn't want to solve all the millennium problems, but he wanted to formalize the statements of the problems in a computer proof checking system. So he gave a talk about this in Cambridge a couple of weeks ago. And 6 of the 7 millennium problems were trivial to formalize, but the Yang-Mills one, he realized that it wasn't actually, it's like the Langlands conjectures. It's not actually a conjecture, it's more like a philosophy. It's like you have to invent some basic theory of whatever, some basic quantum theory that predicts physical phenomena. But, what does it mean to invent a theory? It's not so clear. So sometimes in maths, questions aren't really completely well defined. So, yeah, there's a local Langlands philosophy, and that's what C stands for.